Welcome back, pre-calc. How you guys doing? Hope you're doing well. Hope you're able to actually learn some math during these uncertain and perilous times of early 2020. I got some memes to show you. Okay, I know I already showed you one like this, but I just like this picture of the Mike Wazowski / Sully character. So I'm thinking I could bring that meme back. Here's another one for you. Sleeping in class in 2019, sleeping in class in 2020. This is probably some of you right now. It's only 11:45 in the morning. Some of you are sound asleep as I am awake on my grind recording a video for your education. That's okay. Get your sleep. I definitely sleep in and get a lot more sleep these days, so I am happy about that. Okay, here's what we're really going to work on today. We're going to evaluate these three limits. This is 9.02, evaluating limits. Some of the stuff that we do today is going to be familiar to you. It's going to seem oddly familiar. That's because we've covered it before in the very first quarter. We looked at discontinuities, and in order to do that, we had to kind of use some limit notation. So let me try to remind you or show you what is this thing asking us to do. The practice problems in the quiz are going to say evaluate the limit. Okay, so here's three good examples of the types of limits you're going to be asked to evaluate in this section. The first one here is asking, here's an expression, right? Or you could think of it as a function. It's a cubic, right? I actually have it graphed behind here. Okay, as x approaches 3, as the variable x gets closer to 3, what happens to this? What does this approach? That's how you can think of limits. As x approaches 3, what does this approach? This whole thing. Okay. Same thing down here. As x approaches 9, what does this approach? Okay. And if you're smart, you already see a problem with that, which we'll address. And down here, if x approaches -2, what does this expression approach? And the same problem that happens here. Most of you guys probably can tell what that is. +1 respect to you if you can see what the problem is already. Okay, I'm going to set that aside for now, and let's look at the first one. Okay, so this first one here, I just took this expression, x to the third minus 10x squared plus 16x, and I made it into a function, and I graphed it, and we get this curve. And if we know anything about polynomials, we're not surprised that this is what it looks like, because it's a third, it's to the third degree, right? That leading exponent of 3. So we have 3 zeros actually. 1, 2, 3. Oh, look at that. They hit nice whole numbers. So you could probably figure out how this would factor. It would factor into x and x minus 2 and x minus 8, right? Those would be the three factors. It's got the two turning points. It's got opposite end behavior, right? And the positive end behavior is going to positive infinity. That's because we have a positive leading coefficient of +1, right? I'll review. What we care about is, remember, as x approaches 3, what does this function approach? You can think of this function as the y value of this curve, right? So as we change x, y changes vertically, right? So x changes horizontally, y changes vertically. So we want to know what happens as x approaches 3. Well, let's zoom in here. Here's where x is 2. Now let's approach 3. Watch those numbers. As x is approaching 3, y is getting smaller, right? More negative. And when we hit 3, right there, there it was. When we hit 3 right on the nose, if I can actually control my mouse, come on, there it is. Our y value hits -15. Okay. What if we approach 3 from the other side? Same thing would happen. If we go past 3 and we start approaching 3 from the right, getting smaller and smaller, getting closer and closer to 3, what does our function approach? The y value approaches -15 also, you can see. Okay, so one way to show it is graphically. Okay, we can approach 3 from the right. Sorry, we can approach 3 from the left. We can approach 3 from the right. When we approach 3 from both sides, our y value approaches -15. Okay, we can show that with a table. One of the nice things about Desmos is I can put a table for this function, right? I can plug in an x and I can get an f of x. So let's plug in 2. Let's plug in 2.5, and let's get closer and closer to 3. How about 2.9? How about 2.99? And 2.999? and 2.99999, you can see that as x approaches 3, the y value approaches negative 15. Okay, so what happens when I actually plug in 3? I get negative 15. No surprise. Okay, there's no problems with this function. What if I approach 3 from the other side? So let's go just past 3. 3.0001, 3.001, 3.01, 3.1, 3.54. So we see that from the other side, I approach 3 as I come from the right. As we approach 3 from the right, we also get to negative 15. You can see that the y value is getting closer and closer and closer to negative 15. Okay, so you might think, Mr. Troll, what's the whole point of this? We can tell what's going to happen at positive 3. We just plug in positive 3 for x, and y is 15. So the answer to number 1 is just going to be negative 15, and you'd be right. Okay, for a function like this, where there are no problems and it's nice and continuous and smooth the whole way, no gaps, holes, or skips or jumps, the way that you evaluate the limit is just by directly substituting the x value into the x variables and simplifying. Okay, and in the next video, I'll actually do it for you and show you, even though most of you can already tell what that's going to look like. Okay, where things get interesting, and the whole point of using limits is when we get stuff like number 2. Okay, so let's move on to number 2. I've already have it graphed here in my other tab. Here's number 2. We have this rational function. We spent a lot of time on rational functions in the first quarter, or was that second quarter? I don't remember now. Now we see here that we don't have a continuous function. There's this one side of the function, another side of the function, and they're not really connected. Okay, and of course, we are asked to find the limit as x approaches 9. Okay, and and if x was approaching anything else, right, if x was approaching negative 2, right, our limit would just be 0. If x was approaching 6, our limit would be 0. If x was approaching negative 7.2, our function would be approaching negative 4.237, right? But because we're approaching 9, we see here that at 9, here's the line for 9, right? We see that our function is scooting down to negative infinity on the left side, and at 9, our function is scooting up to positive infinity on the right side. Okay, so our function is actually undefined at 9. We can see that here on the graph, and I can also show you that here. If we make a table of values for this, let's plug in 8 and 8.5 and 8.9 and 8.99 and 8.999 and 8.9999 and 8.99999. What's happening to our y value? Well, our y value is negative 20, negative 50, negative 300, negative 3,000, negative 32,000, negative 329,000, negative. It's getting huge. It's exploding in the negative direction, right? So if I actually plug in positive 9, we have an undefined y value, okay? If I plug in anything just after 9, 9.01, 0.00001, we're going to get something very, very large, and then and then less large, right, as we move down that curve. So 9.01, 9.01, and 9.1, 9.5. Okay, we can see that from the right side, as we approach 9, our value is getting much, much, much larger, right? So that represents us shooting up to positive infinity on this side. You can see here's my point, shooting up to positive infinity on the right side, shooting down to negative infinity on the left side. When we have this thing going on, when it's shooting up to positive infinity from the right and shooting down to negative infinity from the left at the same x value, x equals 9, okay, this limit does not exist right here. As x approaches 9, this thing blows up to positive infinity as you approach 9 from the right. It blows up to negative infinity as you approach it from the left. This does not have a limit. And if you look at the function, it makes sense because if we try to plug 9 in or substitute 9 in for x, our denominator becomes 0. Okay? And when you have a 0 denominator, you have an undefined answer. Okay, so this limit does not exist. And we'll look at that on paper in the next video. Okay, so sometimes you have a nice limit where you can substitute the x value and you get a real number. Sometimes you don't have that. You have positive infinity, negative infinity. You have this giant, what we used to call infinite discontinuity, right? And that's still what it's called. And this limit does not exist. Now let's look at the third one, which I think is the most interesting. Okay, here I have graphed the third function, and we want to know what is the limit as x approaches negative 2. Okay, well, this looks like a nice parabola. So if we approach negative 2, but we look at our function, we say, well, if I plug in a negative 2 there, I'm going to have a 0 denominator, which is causes problems. It should be undefined. So why don't, at negative 2, why don't I see an infinite discontinuity like I did at the last example? Well, let's approach negative 2 from the right and see what happens in negative 1.9, negative 1.99. Oh, what happened there? At negative 2, maybe I need to zoom in here. At negative 2, we get undefined. And you see that little dot where my mouse is empty. It's one of those open dots, right? We have an undefined value. So it's doing the math right. It's plugging in negative 2. It's getting a 0 denominator, and that's undefined. But it looks like our y value is approaching some actual value, right? If you look at our y value, 16.8, 17.2, 17.6. What's our y value approaching? 17.9. Undefined. So it looked like our y value was approaching 18. Okay, and it looks like that's where we are on the y-axis, 15, 16, 17, 18, right? Well, what if we approach negative 2 from the left? 20, look, watching our y value, 20, 19, 19.5, 19.4, 0.3, 0.1, 18.9, 0.6, 0.5, 0.4, 0.2, 0.1. And once we hit negative 2, we're undefined. Okay, so we were approaching 18 from the top, and we were also approaching 18 from the bottom. But once we hit negative 2, we have an undefined result. Okay, but if you write it as a limit, right? If we just find f of negative 2, undefined. But if we take the limit as x approaches negative 2, this is defined, because as x is approaching negative 2, we can see that our y value is approaching 18. Okay, let's show that with a table, just like I did for the other ones. Okay, so there's negative 2 undefined. I'm going to clear all these out just so that they're not distracting us with those other values. So let's plug in something that's close to negative 2. How about negative 1, negative 1.5, negative 1.9, negative, let's just approach 2. Negative 1.99, negative 1.999. What is our y value approaching? 8, 12, 16, 8, 17.89, 17.98, negative 1.9999. Now we're at 17.9989. We're so close to negative 18, but once I throw in negative 2, sorry, positive 18, once I throw in negative 2, we're undefined. Okay, so f of negative 2 is undefined, but the limit as x approaches negative 2 is positive 18. Okay, because as x is approaching negative 2, the y value is approaching 18, and we can see that with a table, we can see that with a graph. Okay, and I'll show you in the next video how we can see that just algebraically, just by looking at the equation. Okay, let's go past negative 2. Let's go negative 2.00001, and we get 18.0001. Well, what about negative 2.0001? We're a little bit past 18 again. Negative 2.001, negative 2.01, negative 2.1, negative 2.5. Oops. And we see that now, as we approach negative 2 from the other side, we are still approaching 18, right? 23.75, 19, 18.1, 18.01, 18.001. We're getting closer and closer and closer to 18 from above 18, and from the other side, we're getting closer and closer to 18 from below 18. So we can see from our table that, yeah, it is undefined at that point, but our function is approaching, the y value of our function is approaching a certain value, right? It is getting closer and closer to 18. It's not going to go past 18 until you go past -2. And if we approach from the bottom, right, we get 18. We're approaching 18 as well. Okay, so that's what a limit is asking. It's not asking what is the value at -2. It's asking what is the value approaching as x approaches -2. So this way we can kind of skirt around some undefined results. We can kind of see, okay, well, the function, it is undefined at -2, but we can see that it's at least approaching -2, so it should be -2. So that's why we use limit notation, is so that we can handle situations like that. So I hope that made sense, guys. In the next video right after this, we're going to do the same 3 examples, but we're going to do them on paper, the way that you're supposed to do them for your assignment. How you can actually figure out what the limit is without having to graph or create a giant table like we did. How you can figure out what the limit is just algebraically. So that's the next video, and I will see you guys in that video. Bye.